All right, welcome to Chapter 11, wherein we will work on the t-test for two related samples. So this is going to be building directly on what we worked on in Chapter 10. Again, a slight variant on the independent measures t-test. So things you're going to need to know in order to fully understand and grasp what we're covering in this chapter is, all things related to the t-statistic. That is, the estimated standard error, degrees of freedom, t-distributions, being able to identify a critical t-value given the alpha degrees of freedom, conducting a hypothesis test with a t-statistic. All of the stuff that we learned in Chapter 9 and some of what we learned in Chapter 10 regarding the independent measures design. So we're now going to be talking about repeat measures design, which is slightly different, and I'll walk through that in just a moment. But just to reintroduce the formula we worked with last time, in the between subjects design, t was equal to the mean of sample mean 1 minus sample mean 2 minus the null hypothesis, which was the hypothesis that the population values were equivalent, or in other words, population 1 minus population 2 equals 0. So this term refers to the null, this term refers to the difference in the sample means, and then the estimated standard error of the mean difference was in the denominator of the t. So in repeated measures design, we're still comparing two samples. But in this case, the samples come from within the same subjects, right? So the simple example of this would be, say, pre and post. So we could take some measurement, then there's some kind of intervention of some type. Something happens to the participants. We want to test the effect of some intervention upon some cognitive process or some behavior or some outcome. And then we test them again. So pre-intervention and post-intervention, two measurements. So we call this within subjects because both samples of data are coming from within the same subjects. Two separate scores are obtained from each individual in the sample. Whereas in the previous design, the independent measures design, we had separate scores coming from separate individuals. Here we have separate scores coming from each individual in the sample. The same subjects are used in both treatment conditions, right? So there's no risk of the participants in each treatment group differing significantly from each other. And this is really important because anytime we recruit participants for a study and randomly assign them to two groups, as in the previous chapter, I gave an example where we were conducting a drug study. We recruited 60 people and we randomly assigned people to either a drug or a placebo group. And so in a case like that, one group could by chance contain a preponderance of individuals who are different on some dimension from members of the other group for some reason or another. Gender is a common problem. Age could be an issue. IQ, pre-existing personality differences. In a repeat measures design, we don't have that problem. We don't have the problem that one of our groups could be different from one of the other groups, therefore providing an alternative explanation for any differences in, say, the sample mean, right? So what if we recruited people for a study, to just piggyback on the same example, it's some kind of drug study, and one of our groups ends up being predominantly female, where the other group ends up being predominantly male. Okay, so we find an effect of a drug on some symptom, okay, and then we can detect a statistically significant difference between our groups. So the intrepid researcher then decides to attribute the difference to the drug. And then someone looks at the demographics of the two samples and says, yes, but in one of your samples you have lots of preponderance of females, and the other sample you have a preponderance of males. Isn't it possible that gender could be having an impact here? And the answer would have to be yes, it is possible, right? So in a repeated measures design, we don't have this issue because we're testing within individuals. We're controlling for any possible differences between groups if we did a between subjects design. We can take it even a bit further if we do a matched subjects design. Now, this is actually kind of rather rare. Most experimental psychological science involves random assignment. So matched subject designs are relatively rare. But this approximates the advantages of a repeated measures design in which we use two separate samples. So this would be a between subjects design in which each individual in a sample is matched one-to-one with an individual in the other sample. So, for example, we could match or control for gender across our two groups by making sure that we have equal numbers of males and females in a group. We could match people on relevant variables like age or IQ or various personality dimensions. But the problem is we can only match on so many dimensions. Participants are not going to be identical to their match, even if they're of the same age and the same gender and the same IQ. There's going to be some other dimensions that they're different on, right? So in a between group design, even when we match subjects, not all the participants are going to be equivalent to their match on some variables. We can always do kind of a quasi-match design. It's actually a pretty good idea when you're in an experiment to make sure that you, say, have equal numbers of females and males between two samples. It's good idea to match for age. But beyond that, that's about as far as researchers tend to go, at least in the psychological sciences. Repeated measures and match sample are kind of related designs, though. They're kind of statistically equivalent methods in a sense, but they use different numbers of subjects because match samples have twice as many subjects as a repeated measure design. And this is another nice benefit of using a repeat measure design, which is you need half as many subjects, essentially, right? And this is going to be the focus of this chapter, repeated measures designs. It's overwhelmingly more common to use repeated measures than matched samples, by the way. I've been doing research for approximately 10 years, and I've never utilized this approach. And the t-statistic we're going to calculate for repeated measure research design is structurally very similar to the other t-statistics. It's essentially the same thing as the single sample t. The only difference is that it's based on difference scores rather than raw scores. So we introduce a new symbol this chapter, D. D stands for a difference score, the difference between one score and another score. Keeping in mind that each of these scores are derived within individuals, like pre and post, right? We measure something at one time point, and then we measure something at a different time point, and then we calculate the difference between these two data points, pre, post, or time 1, time 2, and that's D, the difference score. Right? So when we calculate the mean in a repeated measures design, it's going to be the sum of all of the differences, D, divided by N, the number of individuals. Let's take an example, okay? Let's say I'm going to run an experiment in which I'm going to imagine that a short bout of exercise will increase individuals' capacity to solve anagrams. And if you're not familiar with an anagram, it's a word, phrase, or name formed by rearranging the letters of another word, phrase, or name, right? So, for example, looking at this word right now, Iceman, can you think of another word that you could spell with these same letters if you rearranged those letters? So you may have imagined one. Cinema is one possibility. So right in a between participants design, what we might do is we would give these kinds of words to people, right? And we'd say, okay, your task is to create anagrams. And we would randomly assign people to one of two groups. Okay, we'd assign them to a control group in which they don't do acute exercise. This would be a between participants design or individual or independent samples design. Or we'd assign people to an exercise group. Okay, so we'd randomly assign people to one or the other. In the control group, they wouldn't exercise, and then they would solve a bunch of anagrams. In the exercise group, we'd have them do a bunch of jumping jacks or some yoga or a bunch of push-ups, right? And then they would solve the anagrams. And then we would measure how many anagrams were solved by the exercise group and the control group, okay? So for each individual, we would have a different value, right? Okay, so that would be a between subjects design. Now let's imagine what this looks like within subjects. Okay, within subjects, the same person is going to provide two different measurements now. So we're going to have a pre-point and a post-point. And again, we're testing the same hypothesis, right, which is that acute exercise is going to affect people's capacity to solve anagrams. Maybe it's going to increase it, or maybe it's going to decrease it. Maybe we don't know. So we're looking at some subjects right down here. Here we have 4 subjects, okay? Time point 1 is before exercise. So they get words, they solve anagrams, and these are their scores, okay? Then they exercise. So time point 1, they solve. Then they do some exercise, they jump around a bit, and then we have them do another anagram test, okay? And we derive a different score, and this is D, the D that I just referred to before. And D refers to the difference between time point 1 and time point 2. In this case, it would be time point 2 minus time point 1. X2, sorry. X2 minus X1. D equals. Okay. All right. And so this is this column here. This reflects the difference between time points 1 and 2. And notice there are 4 subjects, so n equals 4 in this case. So if we wanted to derive a mean here, we would sum up all of the d's. So we've got 4, -2, 3, and 1. So that's 7, 8, minus 2, that's 6. And then we've got an n of 4. And that would equal 1.5. Sorry, the handwriting is really bad there. That's even worse. 1.5, is that better? So this would be the mean for D. This would be the mean for the difference score, okay? 1.5. Okay, so let's think about how we'd actually calculate a hypothesis test here for this related samples t-test. We start the same place we started with the other t-tests. We have a null hypothesis and alternative hypothesis. The null hypothesis is that the difference, the population mean difference is 0. Okay, so that's going to be 0. The alternative hypothesis that the difference is not going to be 0. So we start in the same place we started before. Okay, and this is what it looks like if we were to draw these out as distributions. You see in the null hypothesis, the mean is right here at 0. The alternative hypothesis, it's something other than 0. It doesn't have to be 5, just for the sake of example. This figure depicts a 5. But the alternative is going to suggest that the population mean difference is greater than 0, statistically greater than 0. Okay, so that's the alternative hypothesis. So our statistical test is going to test against the null. And if we reject the null, we're going to take that as evidence for the alternative hypothesis, although that's taking things a step too far. All we can really say is that we're rejecting the null, or we're saying data like this would be really, really rare if it's out here under the null hypothesis. Okay. All right, and here's the t-statistic for related samples. So just like on the other t-statistics, this represents the null. So basically suggests that's a 0. So we can not really worry about that one. The t, the values that we're going to end up plugging in are the mean difference score, and then the estimated standard error of the mean difference. So the mean difference score over the error term, right? And as I described previously, conceptually, the difference score reflects potentially signal and maybe some noise, and the error term represents noise, right? So we want a t-value that's positive, and the larger it is, the more likely we're going to be to reject the null, because the noise will cancel out. And so the t is really the signal, right? So if t equals 1, there's basically no signal. We want it to be greater than 1 if we're going to reject the null. Okay, so here's the t-statistic for related samples. Again, kind of don't worry about that. This is what we're going to be plugging in, these two values. So we need to calculate the variance of d, right? So that'd be the sum of squares, calculated just as normally is. We take the mean and then each score minus the mean squared. Then we sum all of those. That's the sum of squares. The degrees of freedom is n. That's the number of individuals, right? Minus 1. In the previous example, we had n equals 4, so degrees of freedom would be 3. That would give us the variance, and then the estimated standard error of the mean difference is right here. The variance divided by n, take the square root of that, and you have the estimated standard error of the mean difference. You plug that in there. The mean difference goes on top, and then you've got your t. Okay, so let's work back to an example here. We've got this data. In the D column, we've got different scores of 4, -2, 3, and 1. So let's work through this. Okay. So here are the scores. So at this point, it might be useful for you to work through this example. So you could pause the video and then attempt to calculate all of these values. We've got a mean here, we've got the sum of squares, get the variance, right? Got the estimated standard error of the mean difference score. Here's your variance formula, here's your estimated standard error formula, and then here's your t observed formula. And then you could also derive the t critical, keeping in mind that n in this case is the number of individuals. The number of individuals is 4. There are 8 data points leading to these different scores, right? But it's the different scores we're interested in. So it's the number of different scores is 4. Degrees of freedom is 3. So go ahead and see if you can work through this, and then pause the video, and then in the next slide kind of reveal the answers and work through each of these. Okay, at this point, so you may have actually worked through those, so you can compare your notes or compare your answers to the answers on this slide here. You should have a mean of 1.5, and this is the result of adding all of these scores up here and dividing by 4. So that's 6 total divided by 4. That equals 1.5. The sum of squares, here's the computational formula. You could use the definitional formula. I've calculated the sum of squares here using the computational formula, but it ends up being 21. Okay, and then variance is SS over DF. That's 21 SS. DF is 3, so it's where N is 4, DF is 3. So the variance is 3. And then we calculate the estimated standard error of the mean difference score, where we have the square root of the variance over n. That's right there. Square root of 3 over 4. 3 over 4 is 0.75, and the square root of 0.75 is 0.87. All right, and then finally, we can calculate t observed. The mean difference score is 1.5. That's the first value we derived up here. Divided by 0.87, that's the estimated standard error of the mean difference. And that's equal to 1.72. So we've got our t observed here. And our t critical is 3.182. That's based off of an alpha of 0.05. Degrees of freedom 3, two-tailed. So clearly, the t observed is not larger than t critical, and we would not reject the null. So note, we underwent the same process that we've learned when we've executed these t tests in previous chapters. Right? First step, define the hypotheses. Second step, define the t-critical value using alpha, deciding if it's a one-way or a two-way, and determining the degrees of freedom. Step 3, collecting the data, calculating the t-statistic, and step 4, rejecting or accepting the null hypothesis. So the numerator of the t-statistic measures the actual difference between the data, and then the hypothesis, the null, right? That's there to illustrate that conceptually what we're testing against is the null, and we're attempting to see if we can reject that null. And then the denominator measures the standard difference that's expected. If the null is true, we're still going to accept some variability and some sample error, right? So we, in the previous example, we had a mean of 1.5. Thinking back to the example, it was that, or the test that we were executing was, or we're testing this hypothesis that acute exercise is going to affect anagram solving. And we had a positive value there of 1.5, so our 4 individuals solved 1.5 more anagrams after exercising. But after we calculated the t-statistic, we determined that even though we saw a 1.5 increase, it was not large enough to supersede what we might expect on average in terms of sample variability and sample error, right? So that very well could have just been sample error. It wasn't large enough for us to say confidently that we observed a statistically significant effect, right? So that's what the denominator is measuring, basically this standard difference that would be expected. If the null were true and there was no effect, what kind of difference will we expect to see down there? Right, and this being noise, statistical noise. So we follow that same 4-step process as the other tests, and then if we do find significant effect, or a statistically significant effect, we can calculate the effect size. This is from a different example, so this is not using the same data as the previous example, but here we've got degrees of freedom of 8. We're using an alpha of 0.05. Just to remember that, in all of these tests, we're doing the same thing. I just want to illustrate this again or point this out again, that we're trying to determine whether our sample falls into this critical region out here or not. Right? And we're going to say that our criteria for whether we determine something is statistically significant is if it falls past these boundaries we've established when we determine the t-critical value. Okay. Okay, so we're not going to introduce any new effect sizes yet. So we're still working with the same three that we've been working with previously. Cohen's d, r squared, and the confidence interval. We've got an estimated mean. Cohen's d involves the mean difference over a standard deviation. Make sure that that's not variance, but is the standard deviation that you use. The denominator there gives us a sense of the effect size. We've got r squared, which tells us the proportion of the variance that can be attributed to the independent variable. In this case, the previous example, that would have been acute exercise. Right? So whatever that value is, it tells us how much of the difference score can be attributed to that independent variable, that intervention. Same formula there, t squared over t squared plus the degrees of freedom. And then finally we can do a confidence interval. Thinking about the previous example, the mean difference was 1.5 plus or minus the t, right? And this is the critical t, not the t that we calculated. We want to use the t, if we're doing a 95% confidence interval. Sorry, I should have mentioned that. Then we would determine the t to use right here by looking in the table or online in a table in our book or online. For 0.05, two-tailed, and degrees of freedom in this case was 3, right? N was 4. There were 4 different scores, so n equals 4, degrees of freedom equals 3, and that t value was 3.182 times 0.87. Right, so we had 1.5 plus or minus 3.182 times 0.7. This ends up being 2.77 basically. And the interval itself then ends up being, and I'm going to do some rounding here, basically negative 1.3 to 4.3. And keep in mind, this was not statistically significant, and this is confirmed or reiterated in our confidence interval. Right, we've got a 95% CI. I'll write this slightly differently. 95% CI with brackets, negative 1.3, 4.3. Note that 0 is a possible value here. So again, we're saying we're 95% certain that the true population value, this mean difference, is between negative 1.3 and 4.3. So we're saying it could go in either direction, or it could include 0. So we don't reject the null, and this is, again, reiterated in this 95% confidence interval here. Okay, in the literature, you report the means and the standard deviation. You're going to report a concise version of the test results, so you report the t-values with degrees of freedom right here. So as such, t, degrees of freedom in parentheses right after the t. And then the value, comma, was something significant or not statistically, p less than 0.05, or you might report the exact p-value. If you're working in SPSS, you'll be given this information. And then the effect size. We've got r squared here. You might be reporting Cohen's d, and you might be reporting a 95% CI. You could report 1, 2, or all 3 of these. Okay, I just want to talk a little bit about some factors that influence the hypothesis test outcome, just some things to think about. The size of the sample mean difference, of course. The bigger the mean difference, the larger the numerator, so the larger the t. And remember, the bigger the t, the better the probability that we're going to reject the null and suggest that there's a statistical difference. Sample size matters. Larger sample size is good. You know, as Frankenstein would say, big sample, good. Big samples mean smaller standard errors. Also means bigger t. right? So in either case, larger t's are associated with bigger sample mean differences. Larger t's are associated with smaller sample sizes, right? This is because of the nature of this formula. So if this number is bigger, we're going to get a bigger t. And if this number is smaller, we're going to get a bigger t. Right? If this is 5 and this is 5, then that equals 1. But if this is 5 and this is 2, then this is going to equal 2.5. So bigger t. Larger sample variance is not good, right? So big variance bad, as Frankenstein's monster would say. Larger standard error, smaller t. So variability is a measure of consistency, right? When treatment has a consistent effect, we're going to see scores cluster together. If we have a drug that's really effective and it affects everybody equally, then we're going to see the different scores are fairly close to each other, that they're clustering, right? There's low variability. This is evidence of a treatment that's exhibiting this really, or exerting a really consistent effect. You know, if a treatment effect is inconsistent, so maybe if it's a drug test, for example, there are individual differences that determine how well this drug impacts an individual, then you might see more variability. And this is an evidence of inconsistency. So your different scores are going to be more and more scattered. Variability is going to be high. So a treatment effect can be significant when the variability is low, but not significant when the variability is high. Even when the mean differences are the same, if variability is different or larger, for example, then we may not have a statistically significant effect. Take this example here. So what we're looking at here, each of these represents a separate piece of data. And say we're looking at the effect of some drug on perceived pain, okay? And we're hoping that our drug is leading to decreases in the perception of pain, physical pain. This is a sample of different scores. So the mean difference score is -2, meaning on average, people report 2 points less pain after taking the drug. Okay, so that's nice to know. But what about the variability? Well, the different scores in this case are consistently negative. Right? Only 2 individuals out of 1, 2, 3, 4, 5, 6, 7, 8, 9 report the same amount of pain or more pain. But 7 out of 9 report a decrease. So this is an example of consistent difference scores. Okay, and here is an example of inconsistent difference scores. We're testing another drug on perception of pain, and we still have a mean difference of -2. Okay, but in this case, the standard deviation is 6. It's pretty large. We've got, again, 1, 2, 3, 4, 5, 6, 7, 8, 9 individuals, 5 of whom show no difference or repeat increases in pain. Okay, and then we've got a couple outliers out here that are pulling the mean in a negative direction, but actually only 4 of 9 are showing decreases in pain. So here we can have a mean that's negative when the majority of the subjects are actually showing 0 or positive values. Okay, so this is an example of inconsistent difference scores in which, compared to the previous example, the means are the same, but the variability is significantly different. So in the first case, we might see statistical significance, but in this case, we won't. And as I've been saying ad nauseum, we occasionally can use a one-tailed test if we have a specific prediction for a related samples design. The null hypothesis and research hypotheses are stated directionally in this case. So it's not that D is equal to 0 in the null and not equal to 0 in the alternative hypothesis, but rather that the D is less than or equal to 0 or greater than and equal to 0 in the null and then the other direction for the alternative hypothesis. So not equal to and greater or less than, respectively, for the alternative hypothesis. And then, as in previous tests, critical region is located in one tail. Okay. So our 0.05 is not split between two tails, but is rather all in the one. But relatively rare, the one-tailed test. Okay, so some advantages of repeated measures designs is that it requires fewer subjects. We're able to study changes over time. It really does reduce or eliminate the influence of individual differences. Double the number of subjects, assign them to random samples, and you're going to end up with some differences, some group differences that you can't control, that you may not even be aware of. And you're going to get substantially less variability in the scores with repeated measures designs or related samples designs compared to an independent samples t-test. And this cannot be understated. Getting subjects to participate in your study is a real challenge. It requires a lot of effort. So if you can cut that number in half and reduce variability, and it doesn't screw your experiment up to do so, then it's something to consider for sure. And there are some disadvantages to repeated measure designs, things we have to look out for. And one is that factors besides treatment could cause our subjects' scores to change during the time between measurements. Right? So we could attribute the change to our intervention or our treatment when in fact it's a product of something else. For example, in the previous example from a few slides back, we talked about a situation in which we predicted that acute exercise was going to increase individuals' capacity to solve anagrams, these word problems. What if it's just that they just got better with practice? They did the first, time point 1, they solved some anagrams, and then when time point 2 came around, they were kind of warmed up and they were in the groove. They had gotten their head around the task, and then they were able to perform better because of the practice effect. So we would have had them exercise and then attributed to the change to exercise when in fact it could have just been practice. So that's an example of how a factor besides treatment could cause our subject's score to change. And this is closely related to the second one here, which is that participation in the first treatment can influence their score in the second treatment, right? So it's an order effect in a sense. If it's possible to counterbalance in a way to control these effects, time-related or order effects, we can do so, but it's not always possible. If it's not possible, then we probably are going to have to relegate ourselves to a between subjects design. Okay, and there are some assumptions for the related samples t-test that we have to pay attention to. One is that observations within each treatment condition must be independent, okay? Within each treatment condition. Obviously, the within individual scores are not going to be independent of each other because they involve the same individual producing them. But one individual should not be affecting another individual's scores within each condition. And then the population distribution of the different scores must be normally distributed, okay? This assumption is not typically that much of a concern unless we have really small samples, like the example I gave before, n equals 4. That's a very small sample, and so we'd be concerned if the population from which these scores are derived was not normally distributed. With the large sample, this assumption can pretty much be ignored. So if we're anywhere over or close to 30 or over, then we can pretty much ignore this one. Okay, so that's it. We will carry on after this, building on these concepts as we move forward into ANOVAs.